All right, the binding energy and the binding energy per nucleon of argon 36, right? Now notice we've got quite a few choices of argon so 18 protons means argon, right? Argon 36 is this guy right here. Okay, evidently there's 38 and there's 40. Okay, notice this is sort of striking, right? Notice that the odd numbers of nucleons are not stable. Remember that isotopic table is natural abundances, right? So things that are totally unstable just aren't in the table. So remember that even numbers, well, I guess you haven't gotten to that video yet, but even numbers of protons and neutrons tend to be stable. The other ones are unstable. I'm sure they exist and we've got data on them. They're just not in this table, okay? So this is the one we want to compare it to. So 35.967546. That's the argon. And then I guess the first thing is to figure out that this thing is, it's 36 total, right? 18 protons. It's got 18 electrons and 18 neutrons, right? And we'll take care of the protons and electrons by using a neutral hydrogen atom, okay? So we're going to turn that into 18 of these guys, right? 1.007825. And then we're going to make just the neutrons. We'll use free neutrons, right? So there we go. Neutrons, remember, neutrons aren't free. 1.00, you got to put in energy. I need a bumper sticker that says that. Neutrons aren't free. Free neutrons aren't free. Okay? Freeing neutrons isn't free. You got to put energy in, right? All right. Would that be disrespectful? Okay, so let's go 18 times 1.007825 plus 18 times 1.008665. And on this side, we have a whopping 36.296820. Okay, the fact that these last digits are the same, we would get a 0 there. That we actually know that that's a 0. It's not like we lost a sig fig there. Okay, so this is if we took it apart, that'd be the mass it has. Put together, it has this mass, right? Okay, so I'm just going to subtract those, right? I'm going to go minus this guy because I don't like negative numbers. 967. So this minus this, right? 967,546. The difference in mass is 0.329274, right? Which means that to tear this thing apart, you'd have to put in, I'm going to multiply by 931.5, and that's MeV per U. You'd have to put in that much energy to tear it apart. So I'm going to go multiply by 931.5. And it's a whopping 306.718731 MeV. Now, we have only 4 sig figs here. This is 6 sig figs. So 1, 2, 3, 4. We have to round it to that. So 306.7 MeV. That's our binding energy. And our Beppen, binding energy per nucleon, we just have to divide by the number of nucleons. And that's what this 36 is, okay? So divide by 36, and we get a whopping 8.5199. So now the greatest difficulty we have is how do we round that to 4 sig figs? 1, 2, 3, 4. We have to round that to 520. And that's MeV per nucleon. Woohoo!